Okay, so good morning to everyone. I'm Katia Liburdi, and I'm a researcher and lecturer in the area of food science and technology at the University of Tuscia, located in Viterbo, around 100 kilometers from Rome. Today, I would like to talk about the effect of lipoxygenase and oxidase enzyme on the olfactory characteristics of some vegetable-based foods. You know, in an ecosystem, plants interact with other organisms, creating a complex network which can influence ecological stability. The secondary metabolite, such as volatile organic compound with acronym VOC, are usually considered a major currency in the plant communication, where they mediate above and below ground interaction between plants and organisms. In general, plant VOC are low molecular weight metabolites with a low boiling point and high vapor pressure. The synthesis of plant volatile compound start from primary metabolite route, and this compound can be grouped into several classes on the basis of their biogenetic origin. These classes include fatty acid, amino acids, and carbohydrate-derived aroma compound. This volatile compound can be emitted from flower, leaf, fruit, and roots into the atmosphere or soil, allowing the plant to interact with its surrounding. The study concerning this volatile component are important, not only in the field of plant physiology, but it is also an interesting topic for food technologies, because plant VOC are major determinant of food flavor and aroma. Moreover, they are of great agronomic importance for food quality. Therefore, my oral presentation is focused on the volatile compound deriving from fatty acid, especially considering the role of the lipoxygenase, a plant exogenous enzyme that regulate the fatty acid oxidation in plant. As I just said, the volatile compound derive from fatty acid, such as straight chain alcohol, aldehyde, ketones, acid, ester, and lactone. And they are basically formed by three processes: LOX pathway, alpha, and beta oxidation pathways. In the LOX pathways, unsaturated linoleic or linolenic fatty acids are oxygenated, leading the hydroperoxide intermediates, which are further converted into volatile aldehyde, alcohol, and diester, that are generally converted with green note odor in fruit and vegetable. LOX is also named linoleid oxygen oxidoreductase, and it has been identified in various cellular parts that produce signaling molecules, and these are involved in diverse functions, which include growth and development, seed germination, response to biotic and abiotic stress, and bonding, fruit ripening, senescence, and cell death. Plant lipoxygenases have been identified in different organs, such as leaves, fruit, roots, and seeds. Regarding its catalytic mechanism, the polyunsaturated fatty acid is converted into volatile compound by the LOX pathway, and they are generally derived from the hydrolysis of membrane phospholipids. The degradation of membrane lipids occurs under normal conditions during physiological and development processes in plants, and may be initiated by biotic or abiotic stress. LOX catalyze the deoxygenation of polyunsaturated fatty acid, producing hydroperoxides that are highly reactive molecules and are readily converted by various enzymes into a series of signaling and defense molecules called phospholipids. It is therefore evident that lipoxygenase is certainly a crucial enzyme in the biosynthesis of the volatile compound. Lipoxygenase produced flavor and aroma compounds that are desirable in many foods, but the enzyme may also give rise to a flower in other vegetable-based food. So, this enzyme pathway has a positive function, especially in fruit. The volatile alcohol and aldehyde, with their greeny, greasy, sweety, and fruity odor, are the major contributors of the sensory characteristic in different fruit and vegetables, such as banana, strawberry, or tomato. The same pathway transferred to other types of vegetable, including legume, has a negative effect on the sensory quality of this kind of food. The hexanal derived from the hydroperoxidation of linoleic acid is primarily responsible for the green bean-like flour of the fatted soy flour, owing to its extremely low flour threshold. Interest in lipoxygenase enzyme present in legume has arisen from their role in the production of volatile compounds associated with grassy bean and rancid on flours, in soybean and dried peas. Of flowers in sweet corn and rice have been also attributed to lipoxygenase activity. And the activity of this enzyme that degrading linoleic and linolenic acid to hexanal and hexanal have been reported also in different leafy vegetables, such as aromatic plant. If you damage, you know that if you damage any green leaf, the odor your nose detects will likely be dominated by a suite of alcohol, aldehyde, ketone, and ester that are derived from the fatty acid released from the damaged membranes and deoxygenated by lipoxygenase. This mechanism also occurs in leafy aromatic plant. In this way, the sensorial characteristic, especially aroma, are altered with a considerable negative effect on the quality of culinary herbs. Herbs and spices grown in various regions of the world, and they have been used especially for culinary purposes. The main commercial form of culinary herbs is the dried product, mainly because dried vegetable material are easy to transport and market and can be stored for long periods of time. Nevertheless, fresh herbs are considered to be more flavorful and superior in quality than dried herbs, even if they can only be purchased from local or regional market. Most of the economically important culinary herbs grown in the temperate zone and include basil, rosemary, and sage that are produced and used in Europe and Mediterranean countries. Over the decade, popularity of botanical product has been worldwide significantly increased. This has led for the demand of higher quality product, since the availability of fresh herbs is limited due to their seasonality, and it is essential to develop better preservation and processing methods. Drying and freezing are the most common method used for preserving aromatic plants. Drying treatment inhibit microbial growth and retard biochemical changes. However, this process can also negatively affect product appearance and lead to loss of aroma and bioactive compound. While the leaf blanching is currently carried out prior to freezing them, blanching is a thermal process designed to inactivate the enzyme in vegetable food responsible for generating of flowers and of odors. Considered that blanching is a heat treatment, a change in color and texture of subjected food can be expected. Moreover, it can lead to thermal degradation of some thermolabile nutrient. Many processors utilize a heat treatment to inactivate peroxidase, one of the more stable enzymes present, and one of the enzymes whose activity is relatively easy to measure. However, lipoxygenase, which is less thermally stable than peroxidase, has been associated with the quality deterioration of many vegetables during frozen storage, due to its involvement in flowers and other production, the loss of pigment such as carotene and chlorophyll, and the hydrolysis of essential fatty acid. Based on what I have said previously, it is advisable to use lipoxygenase as an indicator of adequate blanching, since shorter blanching time may enhance quality retention and provide a better appearance. In my opinion, the biochemical and kinetic parameters of the logs may be used to define the optimum blanching process for aromatic culinary herbs in order to improve their storage stability and preserve their freshness. In our previous paper, the biochemical properties of lipoxygenase extracted from basil, rosemary, and sage have been studied. And the study revealed that the use of lipoxygenase can be a suitable index for managing stabilization technique of aromatic plant leaf in order to inhibit the lipid oxidation without compromising its sensorial characteristics. Before to start with the experiment, all samples were washed and dried, and the leaf sample were frozen in liquid nitrogen and then ground into a powder with a mortar and pestle and mixed with extraction buffer. The homogenate obtained was filtered and centrifuged. After that, the supernatant was collected and the obtained solution was used as the crude enzyme extract. LOX activity was measured using linoleic acid as a substrate, and the formation of hydroperoxide was spectrophotometrically monitored. Moreover, we studied and measured also the effect of pH and temperature on the LOX activity. In this study, in order to establish the enzymatic reaction velocities, linoleic acid concentration were varied in the reaction solution, and the value of both Michaelis-Menten parameters, Km and Vmax, for each type of crude enzyme extract were calculated by means of a nonlinear regression procedure. In the present study, all obtained extract oxidized linoleic acid. The plot of the LOX kinetic assay followed the hyperbolic behavior of the Michaelis-Menten equation, and the kinetic parameters obtained are reported in table. The Vmax value in the table, you can see that the Vmax value measured for basil was higher than that measured in rosemary and sage, whereas the Km for rosemary and sage was much higher respect to the basil. Regarding the optimum pH and temperature, all of the LOX crude extract, regarding especially primarily the pH, first the pH, all of the LOX crude extract generally showed maximum activity at pH values between 5 and 6. More specifically, the optimum pH-dependent activity of LOX from basil and sage was at 5, at pH 5, but LOX also proved to be highly active at pH 6. The activity then decreased sharply toward the higher pH value, the alkaline side, on the alkaline side, for the crude extract from the sage sample. No activity was observed either below pH 2 or above pH 9 for all crude extract. The optimum temperature for linoleic acid oxidation was 40 centigrade for all crude extract. At 60 centigrade, approximately 80% of LOX activity was retained by the sage extract, while the crude LOX extract of basil and rosemary lost 50 and 65% of their activity respectively. Above 60 centigrade, all LOX activity decreased with increasing temperature, and the enzyme was completely inactivated at 90 centigrade. Concluding, in this study, the LOX from basil, rosemary, and sage leaves was characterized using linoleic acid as a substrate. The crude extract examined presented several kinetic properties, with basil that expressing the highest specific activity. The optimum pH value for LOX extracted from both basil and sage ranged between 5 and 6, while the optimum pH for rosemary was 6. All crude extract at 40 centigrade showed the optimum of temperature. The preliminary results regarding the mechanism of lipoxygenase inhibition can serve as a starting point for future in-depth studies, with the aim of implementing effective technological strategies for inactivation of this enzyme. By inactivating LOX, it may be possible to prolong sensory shelf life and improve aroma retention for minimally processed herbs. Thank you for your attention.